continue with Laplace transforms. Before starting using Laplace transforms in the vibration, first it's better to review two important theorem in Laplace transform. The first one is the initial value theorem, and the second one is the final value theorem. According to the initial value theorem, the initial value of the response xt in the time domain, or x at t is equal to 0, is equal to the final value of the response in the Laplace domain. I mean, when you have the initial condition at t is equal to 0, and you know that how much is the displacement or the response at t is equal to 0, it's equal to the final value of the response in Laplace domain. Or vice versa, you can find when you have the xs, or you have the response in Laplace domain, you can find its final value when s goes to infinity, and you can find the value for this limit, and it's equal to the initial value in time domain. Another theorem in Laplace transform is the final value. The final value of the response in time domain, or steady state value, or when t goes to infinity, the xt is equal to the initial value in Laplace domain. So again, if you have the response in Laplace domain, for example, you have the xs, when, once you substitute s is equal to 0, you can extract the value for the steady state value in time domain. So you can use these two theorems for the cases that you have the response in Laplace domain or in time domain. Of course, usually we use this theorem to find the response in time domain. So we can assume that we have the response in Laplace domain, but it's sometimes it's not possible, or it's very complicated to find the xt, or using the Laplace inverse transform. And we want to find the, for example, the steady state value of the response. So you can use this theorem by substituting s is equal to 0 into your Laplace domain response. You can find the final value of the response in the time domain. So these are the application of these two theorems. And now we can use the Laplace transform to find the response. Again, we can refer to the equation of motion for a system with single degree of freedom. This system is subjected to a unit impulse, for example. So the equation of motion will have a non-homogeneous term delta t, which is the impulse. We have the equation of motion. The homogeneous part is mx double dot, which m is the mass of the system, cx dot, which c is the coefficient of damping, plus kx, which k is the stiffness of the system. So we can use the Laplace transform equation. We know that the x double dot, or the second derivative of x with respect to time, if you want to find the Laplace transform of this x double dot, it's equal to this term as s squared multiplied by xs, which this xs is the Laplace transform of x, minus s times by x naught, which is the initial value in time domain for the displacement, minus v naught, which is the initial value for the velocity in time domain, plus c instead of x dot. This time we should find the Laplace transform of x dot, which is sxs, and this xs is the Laplace transform of the response minus x naught. And x naught is the x at t is equal to 0, or the initial value for the displacement in time domain, plus k times by xs, which xs is the Laplace transform of xt. So you can see this is the Laplace transform. And finally, delta t in the right hand side of the equation, delta t, the Laplace transform of delta t is equal to 1. If you want, you can refer to the previous slide for the tables. Here, you can see delta t, for example, here, you can see that the Laplace transform of f double dot, of course, here instead of f, we have x double dot, no different. We will have s squared times by fs, which is the Laplace transform of f. So instead of x, as I told you, we have x. Here we have f minus s times by the initial value in time domain for the displacement minus initial value for the velocity in time domain. And also for x dot, we use this equation, f dot, which is s times by fs minus f naught, or the initial value for the displacement in time domain. So we are using, in fact, these tables to find the Laplace transform of this equation. Now we have this Laplace transform. We can simplify this for x. Here you can see we will have m times by s squared times by x plus c times by s times by x, and finally plus k times by x. So we will have ms squared plus cs plus k multiplied by xs, which this xs, as I told you, is the Laplace transform of the response in Laplace domain. And our purpose is to find this xs. As you can see, we convert one ordinary differential equations into an algebraic equation. And now we can move the other terms to the right hand side of the equation. We have m times by minus s times by x naught, m times by minus v naught, c times by minus x naught, and finally we have 1 in the right hand side. So if we move them to the right hand side of the equation, we will have mv naught plus ms plus c times by x naught plus 1. Now we can solve this equation for xs and obtain the value for the response in Laplace domain. By assuming that the initial condition is 0, it means that x naught and v naught are equal to 0. Now we can find xs. From here, we can conclude that xs is equal to 1 divided by ms squared plus cs plus k. Of course, if the initial condition was not equal to 0, here instead of this 1, we had, for example, another number, another value. So no different, the procedure is the same. I mean, if you substitute here for x naught and v naught, for example, substitute the numerical values and simplify this term in the right hand side of the equation, here instead of this 1, you will have, for example, 10 or another value, numerical value. But the procedure to the solution is to find the response is the same, no different. Here we will find the response for the case when the initial conditions is 0. So from this equation, we can conclude that xs is equal to 1 divided by ms squared plus cs plus k, which the denominator of this fraction, as you can see, is the coefficient of xs in the first equation. Now we need to find xs in time domain, or in other words, to find the response in time domain, we need to use the inverse Laplace And for this purpose, we need to find the subfractions for xs, and you will see how we can find the inverse Laplace of xs without using the integral or without using the formula. Now we can simplify this equation. The denominator, you know that we can write it in the standard form. In the standard form, when the coefficient of s squared, you know, this is the equation of motion, similar to the equation of motion, mx double dot plus cx dot plus kx. So this m is the coefficient of x double dot, c is the coefficient of x dot, and k is the coefficient of x. Now, if we divide or if we factor m and it comes out from the parentheses, the coefficient of s squared is 1. The coefficient of s will be c divided by m, and the coefficient of the constant part is k divided by m. Instead of c divided by m, you know that we can write 2 cosine omega n, and instead of k divided by m, we can write omega n squared. There is no different. I mean, in the real problems, in the exam, for example, or in the examples, you will see that instead of this m, c, and k, we have some numerical values. So no different. You can substitute the numerical values and calculate here. Because I want to extract the roots of the denominator as a function of cosine and omega n, so I try to write it in the standard form. So you can write directly from this form. You don't need to, I mean, extract the standard form. But here, because I want to find the roots of the denominator as a function of cosine and omega n, or damping ratio and the natural frequency, I'm using this format. So it's up to you, no different. You can use any other format that you want. So here I wrote this in this form. And now we can assume that the denominator is this term, s squared plus 2 cosine omega n times by s plus omega n squared. And the numerator is 1 divided by m. This term is the numerator of the fraction. Now xs is equal to this fraction. We can expand this xs as a 2 subfractions, as you can see, c1 divided by s minus s1 and plus c2 divided by s minus s2. So we can write xs, or we can express in partial fractions as this form. And now we need to find or calculate c1 and c2. And also s1 and s2 are the roots for this for the denominator. And in fact, according to this form, we can easily write s1 and s2 as a functions of cosine and omega n. So as I told you, we can find c1 and c2. You know, when you want to calculate this fraction, c1 and c2, of course, from previous slide, in fact, here in this slide, you know that this term is equal to this term. So if you want to simplify this partial fractions, it's equal to the numerator of this fraction multiplied by the denominator of the second one, and the numerator of the second fraction multiplied by the denominator of the first. So it will be c1 multiplied by s1 minus s2 plus c2 multiplied by the denominator of the first fraction, which is s1 s minus s1 divided by s minus s1 multiplied by s minus s2. The denominator is the same as this term, s squared plus 2 cosine omega n s plus omega n s squared, as I told you. But the numerator must be equal to 1 divided by m. Okay, so because we assume that this is the numerator of this fraction, 1 divided by m in the numerator, and the denominator is ss squared plus 2 cosine omega n s plus omega n s squared, and it's equal to s minus s1 multiplied by s minus s2, which s1 and s2 are the roots of this equation. Now we can find c1 and c2 from this equation, new equation that I write here. This is C1 multiplied by S minus S2 and C2 multiplied by S minus S1. It must be equal to 1 over M, or this is the numerator of two-hand side of the equation. Now we can simplify this. C1 multiplied by S plus C2 multiplied by S. So it will be C1 plus C2 multiplied by S. C1 minus C1 multiplied by minus S2, and C2 multiplied by minus S1. So it will be minus C1 S2 plus C2 S1, and it must be equal to 1 divided by M. In the right hand side of the equation, we don't have S, but in the left hand side, we have S. So we can conclude the coefficient of S in the left hand side must be equal to 0. It means that C1 plus C2 it must be equal to 0. And in the right hand side, the constant part is 1 divided by M. And in the left hand side, it's minus C1 S2 plus C2 S1. Now this term must be equal to by minus 1 divided by M. Now we have two equations with two unknowns, C1 and C2. As you can see, we have two equations, and we can easily solve these two equations to find C1 and C2. And also, as I told you, S1 and S2 are the roots of the characteristic equation. Here you can see S1 is equal to minus cosine omega n plus I omega d, and S2 is cosine omega n minus I omega d. Now we can find C1 and C2 from the first equation. This equation, we can conclude that C1 is equal to minus C2. And from the second equation, you can substitute, for example, for C1, you can substitute minus C2. And for S1 and S2, you can substitute from here. And finally, if you simplify this, you can conclude that C1 is equal to minus C2 is equal to 1 divided by 2im omega d, which m is the mass of the system and omega d is the frequency of the damped system. This is the omega d, or the imaginary part of your roots. Now you can substitute into the xs in this form. You can see xs, or the response in Laplace domain, is equal to 1 divided by 2im omega d, because C1 and C2 are equal, only there is one negative for them. So here we will have 1 divided by S minus S1 minus 1 divided by S minus S2, which S1 and S2 are here, are defined here. Now we can write, and we can use the tables in the previous slide to find the inverse Laplace of this xs. And you know that this term is a constant value, so it will appear in the time domain exactly as the same. But the Laplace transform of this term, 1 divided by s minus s1, is equal to the exponential of s1t. We have one negative, again here one negative, and the inverse Laplace of this fraction, 1 divided by s minus s2, the Laplace inverse of this fraction, according to the tables in the previous slide, is exponential s2t. And if you substitute s1 and s2 from this table, from this results, you can simplify. Exponential of s1t, for example, is exponential of minus cosine omega n plus I omega dt. And if you expand this term, we will have exponential minus cosine omega nt. And here it will be exponential I omega dt minus exponential minus I omega dt. So this is finally the response in time domain. And also, you know that you can use, of course, here I write in sinusoidal form, because you know that this parenthesis in fact is the definition of the sine by using the sine function. Or you can expand this. You know that exponential of I omega dt, for example, is equal to cosine omega dt plus I sine omega dt minus, and this term again is cosine omega dt minus I sine omega dt. And if you simplify this, you can extract this term. And finally, this is the response in time domain. Okay, I hope it makes sense for you. Of course, we will solve some numerical examples and you will see it's not very complicated. It's very easy. You can easily solve this. And the main challenge for you in these type of problems is to find C1 and C2, I think. How to obtain C1 and C2, you need to find the subfractions. And as you can see, in the problems when you are using the Laplace transform, you don't need to solve any ordinary differential equations. And the main challenge for you, as I told you, is to calculate these subfractions and calculate C1 and C2, the numerator for the new fractions, and find the inverse Laplace transform. Okay, so you can easily find the response in Laplace domain, and by using the inverse Laplace, you can find the response in time domain. Okay, we continue with one example. A mass m moving with velocity v sub 1, this mass, the small mass m, strikes the mass uppercase M of a damped STOF system as shown in figure, and gets attached to the mass uppercase M after the impact as shown in figure. Find the resulting displacement response of the system. So we have one mass with mass lowercase m, which is going down with the velocity v1. This system is initially at rest, and when this mass m with a lowercase mass m strikes the uppercase mass m, it will attach to this system, and the system will start to vibrate about the static equilibrium position. So we can write the equation of motion after the impact. Because both mass will convert into the same mass, we can easily write the equation of motion, which is lowercase m plus uppercase m multiplied by x double dot plus kx plus cx dot is equal to 0, or it's equal to the impact that the impulse that is created due to this impact. Okay, and I will explain that we will have two options in this type of problems. I mean, we can consider the impact in the initial condition, or we can consider as an external force and in the non-homogeneous term. So it's up to you, and I will explain the both methods in this example and in the next example. But here we have one completely inelastic impact, because after the impact, the mass m, or the small mass, is attached to the big mass m, and we will have an inelastic impact. So we can write the conservation of momentum. Before the impact, we have mass times by the velocity. The momentum is equal to mv, as you know. The lowercase mass m has the velocity of v1, and the uppercase mass m is initially at rest, so its velocity is 0. After the impact, the momentum will be remain the same, but the mass is m plus m, or the lowercase m plus uppercase m, multiplied by vf, which vf is the velocity of this system after the impact and the initial velocity of the system when it starts to vibrate about its equilibrium position. From here, when this term is 0, we can easily find that the vf is equal to m multiplied by v1 plus m plus m, divided by m plus m, sorry. This vf is the velocity of this system exactly at the moment after the impact. Or we can consider this is the initial velocity of this system when it starts to vibrate about this equilibrium position. Now we can use this term as an initial condition and solve the equation of motion. As you can see, and as I told you, this is the equation of motion because this is the mass of the system, m plus m multiplied by x double dot. And this is a single degree of freedom. You can easily extract the equation of motion, and it's cx dot plus kx. It must be equal to 0. But the initial condition, because this impact only causes a change in the velocity of the system, so the displacement, the initial displacement will be assumed 0. Okay, so as you can see, the initial displacement is 0 and the system was at rest, but the velocity, the initial velocity is vf. As you can see, this is the vf that we calculated from the conservation of momentum, and we can consider it as the v naught, or the initial velocity. Now we have a simple ordinary differential equation with two initial condition, x naught and v naught, which x naught is 0 and v naught is vf. This is the vf. And if you had the numerical value, you can easily substitute and solve this equation as an equation of motion for the system and find the vf. Sorry, find the response because we calculated the vf. Okay, so this is the procedure to calculate the response for the system after the impact. As I told you, you have another option, and in this option, you can consider the impact as an external force. And you will see in the next example how we use it. If you consider it as an external force, here we have one impact. So here the initial condition, you can consider that this initial condition is 0. I mean, V naught was in that case was equal to 0, but the equation of motion here, instead of 0, we will have some terms, and it's some terms which are related to this VF, and the VF will be appear here. Okay, but in the next example, I will explain how we can use the second option. Okay, in this example, the next one, again, we have a mass M, again, the same system, but this time we don't have an inelastic impact. See, a mass with mass lowercase m moving with velocity v sub 1. Here, let me show this mass with velocity v sub 1 strikes the mass with uppercase m, this mass, of a damped STOF system as shown in the figure. The impact is perfectly elastic this time. So it's not inelastic. It means that after the impact, the small mass is not attached to the big mass. So that after the impact, the mass M rebounds with velocity v2. So after the impact, as you can see, the uppercase M has the velocity v2, uppercase v2, and the lowercase m has the velocity lowercase v2. So this is an elastic impact. This time we want to find the resulting displacement response of the mass m, uppercase M, or the mass of this system, or the response of this STOF system. The equation of motion easily is uppercase M x double dot plus cx dot plus kx. In this case, and in the right hand side, I will discuss that what should we put here. I will discuss that what is the non-homogeneous term, and I will discuss that two different cases. But the equation of motion, the homogeneous part is this mx double dot plus cx dot plus kx. And as you can see, because after the impact, the masses are not attached to each other, and we only have this uppercase mass m. So the equation of motion, the mass is only this term, and we don't have the lowercase mass m. Okay, now we can extract the relation for the velocity of the particles after the impact. So based on the conservation of the momentum law, as I told you, the initial momentum is the mass times by the velocity. Before the impact, we have lowercase mass m multiplied by lowercase v sub 1, uppercase mass m multiplied by uppercase v sub 1. After the impact, the momentum is again the mass multiplied by its velocity, the uppercase mass m multiplied by its velocity. So from here, we can conclude that m times by lowercase v sub 1 minus v sub 2 is equal to minus uppercase m uppercase v sub 1 minus v sub 2. So we can use this is as the first equation. And the second equation will be extracted from the conservation of kinetic energy, because this is an elastic impact. So we can use the principle of the conservation of kinetic energy. So the kinetic energy, as you know, for a particle is equal to half times by mass times by its velocity squared. So before the impact, we will have one kinetic energy for this particle plus the kinetic energy of this particle. It must be equal to, after the impact, the kinetic energy for the small particle and the kinetic energy for the big particle. And finally, we can simplify this in this form, as you can see, and we can expand this term. This half will be cancelled out with this half. In the right hand side, you know that v1 squared minus v2 squared is equal to v1 minus v2 multiplied by v1 plus v2, this term, and we call it second equation. From the first and second equation, if you substitute here, you can see we have in the second equation, we have m times by v1 minus v2. And here in the first equation, we have the same term, which is equal to minus uppercase. If you substitute from equation 1, this term will be cancelled out, and we can conclude that v1 plus v2 is equal to uppercase v1 plus uppercase v2. And finally, from these two equations, or if, for example, we call it, for example, equation 3, equation 1 and 3, by solving them, you can conclude that V2, the lowercase v2 and uppercase v2 can be obtained. And also we use this point that the velocity of the system is zero initially, because this is initially at rest, this system. So V1 is equal to 0. The system is initially at rest. So we will have two unknowns, V2 and uppercase V2 are the two unknowns from these two equations. You can easily solve them and obtain that the velocity of the small particle after the impact is this term, lowercase v2, and the velocity of the big particle after the impact, this velocity is uppercase v2. This is the after the impact. Now we can use the impulse equation. We have a linear impulse equation. You know that the linear impulse equation from the dynamics is ft dt from 0 to t. It's equal to this term, the value of the impulse during the impact, and it's equal to the velocity of the system multiplied by its mass, which the mass of the system is uppercase M, and you can substitute here, and now you can put this impulse, the value of this impulse, in the equation of motion. Now let's substitute. If you substitute this value for the impulse, you know that this is the value of delta t. And now you can solve this equation with this amplitude for the initial condition 0. As I told you, in this case, we assume that the impact is appeared as an external force. So we deal with one non-homogeneous equation, as you can see, but the boundary conditions, or sorry, the initial conditions is homogeneous, or they are 0. And we can easily find the xt by using the impulse function response and substitute for omega and omega d, and you can easily find the response. As you can see here, instead of this f, in fact, is this term. You can substitute here for f. Omega n, psi, and omega d are obtained from these terms, the coefficients of the homogeneous equations. This is the second case. As I told you, you can use this method, or you can also consider the impulse in your initial condition, similar to the previous example. So in this case, the equation of motion is homogeneous, but the initial condition x at t is equal to 0, but x dot, the velocity at t is equal to 0, is equal to the velocity after the impact. This is the uppercase v2 that we calculated in the previous slide, and this is the velocity of the uppercase m mass after the impact, and you can use it. And finally, you can solve and calculate the response by using this initial condition. You know that the response of this equation, because this is an homogeneous equation, is only include the homogeneous response. You need to obtain or form the characteristic equation, find the roots of the characteristic equation, alpha 1 and alpha 2, and then the response is equal to C1 exponential alpha 1t plus C2 exponential alpha 2t, and C1 and C2 will be obtained from these two initial conditions, or you can substitute into the formula like this for V naught, which this V naught is in fact this velocity V2. And you can substitute here for psi and omega d. You can substitute from the equation, calculate them, and you will see the response from both methods are the same, because the system is the same, and only we change our initial assumption. I mean, in the first solution, we assume that the impact is an external force. So the initial condition was 0. But in the second solution, we assume that the impact is create some initial conditions, and the equation of motion was an homogeneous equation. But the response for both of them is the same. Okay, we can wrap up this session, and again, we will continue on tomorrow. Thank you.